that will illustrate this lesson during column test experiments.
Okay. Hello, everybody. My name is Oudega from TU Vienna. So yeah, I will tell something about the column test that we did with PFAS and porous media and the lessons we learned. So here's the column test setup. So we have an injection solution containing 10 different PFAS. This is then transported by a polypropylene tube to the column, which is then filled with sand. And yeah, the injection solution is pushed through by the pump, and the samples are then taken from the effluent. So the column is 50 centimeter long and 7 centimeter in diameter. We've done these tests with both with quartz sand and with natural soil from the study area, which I will talk about in a following presentation. So we had a mix of 10 PFAS at 2.5 microgram per liter, and bromide was used as a conservative tracer as a comparison. We had 38 effluent samples and also 5 samples from the injection solution itself. And after the experiment, we washed all the materials with methanol, including the injection solution flask, all the tubes, and also the column itself, and also the sand. So the injection solution was 2 pore volumes in volume, and it was continuously stirred to get a homogeneous concentration distribution. Samples were then collected over the time of injection, either by pouring from the top or by using a pipette at the depth of the injection tube, which was at the bottom of the water column. And 5 samples were taken during injection. And these samples were then measured with liquid chromatography. Here are the results of the injection solution monitoring. So on the top left, we have PFOA, which kind of behaved as we expected. So in blue, we have here the pouring technique, and in orange, the pipetting technique. And the target was a mass of 3.75 micrograms. So yeah, as you can see, PFOA had a decent result. But these other 5 PFAS were very surprising to us. So we see that especially the longer chains, such as PFDODA, have extremely high concentrations when using pouring from the top, which probably means that these PFAS were all aggregated at the air-water interface. And of course, it is known that PFAS do this, but we thought because we were stirring the injection solution and thereby breaking the air-water interface, this wouldn't happen or wouldn't happen this extreme. And yeah, we found, unfortunately, that it's otherwise. And it's even sometimes so large that the concentration at the bottom of the water column gets lessened as well. And you can imagine that this has a large effect on the transport characteristics of the solution. And also it makes it more difficult to close the mass balance. A little bit about the effluent now. So these are the breakthrough curves of what we found at the effluent. The dotted blue line here is the electrical conductivity. So this is a measure of bromide. And we found that different PFAS behave differently. So we have first a group that is behaving very conservatively. So it has the same kind of breakthrough pattern as the bromide. And PFBEA is here a good example of that. Then we have a second group, which is semi-conservative. So it's maybe only slightly delayed compared to the first group. And the peak concentration might also be a little bit lower. Then we have a third group, which has a much later breakthrough and a much lower peak concentration. PFOS is in this group, for example, and also this 9CL-PF3ONS. We interpret this as being absorption-desorption behavior. So we think that the PFAS is interacting with the soil, then it gets back into the water, it's transported a little bit and gets back into the soil and so on. And thereby it's breaking through later. And then we have a fourth group, which is complete sorption. So these PFAS were not found in the effluent almost at all. And these are mostly the long chain PFAS. So this is the mass balance for the experiments. Again, PFOA was here this semi-conservative, but you can see that most of it is found in the effluent. So if there's some sorption, it's probably not permanent. And we find in the sand only a few tenths of nanograms. Compare this to a long chain such as PFAS, where only 1% is found in the effluent. And we have over 2,000 nanograms at the bottom of the column. Then we did the second experiment. We had the injection for the same amount of time, but then we had a flushing of 4 weeks instead of 2 days. And then you can see here at the sand that this large amount of PFAS is moved out. And also, if you look at these 4 PFAS, for example, there's nothing found in the sand after this 4 weeks. So another way to show this is the bar graph, which shows the PFAS we found in the porous media. So this is group 4, a long chain PFAS. And this showed here that almost 70% is flushed out after 4 weeks of flushing, which kind of shows the significant absorption and also implies that even in this group where it seems to have complete sorption, that even this sorption is not permanent.
Can you be passed, please?
This is the finish.
Perfect. Perfect.
I will leave it to you.
Quickly for the conclusion. So in this project, we have provided an implementation of the global methods for PFAS. To summarize rapidly, so the TF is, we have demonstrated this is a rapid analysis and less expensive than the target analysis with, of course, this LOQ limitation. For the data set, we recommend a careful initial characterization of the samples. For the AOF, we demonstrated that we have significant differences that can result in a non-exhaustive selectivity of AOF. So here, monitoring methods need to be carefully selected and applied, taking into account the variability and the complexity of PFAS for accurate and comprehensive assessment. So thank you for your attention.